I told you I would say something about energy storage, so here's a little bit about energy storage. The first thing that you would say is, well, I can just hook up a battery and make a energy storage that way. And one could try, but there's a fundamental reason for why that's not so terrific. If you think about what happens when we perform combustion of a fossil fuel, we take a liquid and we burn the chemical bonds in it. And for every chemical bond, we get a few electron volts of energy, a certain amount of energy for every bond. When we work with a battery, all we do is we push an ion in and out. Okay? But we don't really fundamentally make and break chemical bonds. And for this reason, the energy density of a fuel is about 100 times better than the energy density of a battery. Now, it turns out that when you do combustion, it's only got a certain efficiency, so in the end it's about a factor of 30. But the difference of a factor of 30 between a battery and a fuel is a big difference. And that's why we use combustion to power things. So the question then becomes, could we not use combustion in order to store energy, but to do it with a good power efficiency? So this is then the topic of artificial photosynthesis. Plants, algae, take photons from the sun and they make fuel. Why not use those? Well, we should. That's a good thing to try and do. To make biofuels in the right way is a reasonable thing. But the plant or the algae has lots of other things that it wants to do besides harvest energy. It's bathed in photons. And so it uses the photons, but only to a certain degree. The power efficiency of the fastest growing plant is approximately 1/2 of 1%, 0.5%. What it means is that if we want to use natural photosynthesis, we have to devote a lot of land area. But regular photosynthesis itself, the natural, has this function of about 0.5%. But in principle, we can think about making photosynthesis work with an artificial material, and there's no reason why it couldn't be 10% power efficiency. So our goal should be to try to make an artificial photosynthetic unit that takes sunlight, and instead of making electricity the way the solar cell does today, we would be feeding into it, for example, carbon dioxide and water, and making a fuel. Then when we burn the fuel, we make carbon dioxide and water. Then we take the carbon dioxide and water, we make fuel again. It's a complete cycle. And then we've made a carbon cycle of the future. So we better go and try to understand how nature does photosynthesis and then learn how to do it better. And it turns out nature is full of all kinds of tricks. And when we study it pretty carefully, what you find is this is really hard to do. So I'm going to skip a few things here because I'm a little conscious of time. But what I want to say is that we tried in my lab today to build little units of artificial photosynthesis in which every scaling law that I just told you is used. We make a tiny quantum dot embedded inside a quantum rod. We adjust the quantum confinement, the energy levels, such that a photogenerated electron hole pair will send an electron to one direction in this crystal, and the hole will stay in the other side. We attach catalysts to the different parts, and then in this case we're trying just to do the water splitting reaction at some kind of reasonable power efficiency. So that's an exercise that we're trying to practice with. If we could get good at this, we could try to tackle the CO2 reduction problem, for example, even tougher. So all the scaling laws come to work in that place, and I better skip this stuff because it's lots of pretty detailed stuff that I don't think I should do. But I do want to say, here's the algorithm that we've been discussing tonight. Design using scaling laws, build on the nanoscale, design using scaling laws, measure at the single molecule level. And if we perform that as a kind of virtuous loop, we can make a whole variety of energy technologies where they have been made truly at the foundations at which the levels of energy conversion occur. So there's a lot of promise in them. And I hope that gives you a feeling for the connections between nanoscience and the carbon cycle. This is just a picture of me with my current group members. Of course, over some 20-something, 25 or more years now, there have been a lot of different people, but I think it's just kind of fun always to look at these pictures where you can see people coming from all over the world to work together in a very happy way. Actually, 2 World Cups of soccer ago, my research group had in it representatives from 7 out of the 8 quarterfinal countries, which meant nobody got any work done for a long time. And we're still trying to recover. One last thing I want to say. It was really, I'm really happy to be back in Greece and to be visiting here. I was visiting for a family reason in February, and when I talked to everybody, they were so depressed. And I know it must be very hard because so many difficult things are happening. So on the plane home, I thought, well, I'd like to just do something. So I did the only thing I knew how to do, which is I wrote a little article which talks about what Greece might, it takes the point of view of a journalist writing an article in the year 2030 about what things happened in the year 2012, which set Greece on a course such that in the year 2030 it was now an economic miracle. And however improbable you may think that is, I actually, what I saw today at AIT made me think, yeah, that could work. And so I believe that's possible. There's an incredible talent here, and there's a lot of resource and a lot of capability. So if it all comes together in just the right way, I'm sure it's possible to do that. And if you're interested in this, this little kind of, it's written as a kind of fairy tale. It's probably very naive because I'm not, embedded in the world here and I don't know all the specifics. But for me, it was a therapeutic experience to write it on the plane, and it's there for you if you want to go look at the March 27 Sunday K magazine from Beth and me. And I'd like to thank you for your attention. Do ask questions. I'll feel mortified if you don't. So. Yes, please.
So, how close do you think we are? How close do you think we are from exporting our solar energy, maybe to Germany, storing it and exporting it?
Well, it's a fact that Greece has a lot of very nice photons coming down from the sun, and every photon is precious. And why not use them? And I think a partnership with Germany in solar energy is just an obvious thing to try to explore. The Germans are now getting a lot of energy from solar, incredibly, but there's lots of issues of concern to them. They made an incredible investment to build up an industry, a solar industry, that is struggling quite a bit at the moment. Maybe there's an opportunity there where there can be, where even photovoltaics today, through high voltage DC transmission lines, can send energy to other parts of Europe or can provide more energy to Greece. And so I think it's something really that to really be thinking about solar energy in Greece. It's a good thing to do. How close? Well, things could be done now. Now. Yes. 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 For photosynthesis. Organic photosynthesis. Yeah, so organic photosynthesis, that's right. The issue on organic photosynthesis is going to be photostability. In the natural biological system, of course, the chromophores are exchanged on some regular basis because there's a whole cell machinery to do that. I think that it's a very important topic to investigate. I didn't present an argument here, but I have a kind of scaling law argument that I could make about why I believe the light absorbing unit should probably be at least consisting of a few hundred atoms. It has to do with the fact that every time a photon gets absorbed, there's a certain probability that something wrong will happen and a bond will break. But if it's distributed over a couple hundred bonds, those probabilities become small enough that things can last for a long time. So if I were working on organic chromophores, I'd be trying to work with ones that are fairly delocalized, distribute the excitation. But I also would say this, that in terms of science ideas, it's really important to pursue the organic photosynthesis. Equally important would be to try to find a case where in an artificial system you could have repair take place. I know it's possible. No one knows how. Yeah. In the back. Yeah.
I'm wondering, with all the wind and the sun energy that we've got at the moment, one would think that how to store that energy would be one of the first things we would have internationally figured out till now. And yet it sounds like, if I understood you well, that you said that's still a problem. And I wonder why. Where practically, I mean, we figured out how to get to the moon. Why can't we figure out how to store energy? Is it money? Is it will? What is it?
Well, it is a hard thing to do. And one of the things that I had a slide showing earlier, the progression of solar energy from thermal to photovoltaic and then artificial photosynthesis. And it turns out that that is a progression that involves, in this case, really learning how to take photons and create more organized forms of matter. It's a bit of a challenge for us to do. Now, look, in answer though to your question, is there a social dimension to it? I have the great pleasure in life to be working in Berkeley, and one of the famous scientists there was Melvin Calvin. Melvin Calvin discovered the Calvin cycle, which is how carbon gets fixed by biological systems. And in 1978, I think, when I was supposed to graduate from high school, Calvin wrote an article saying, I don't see any reason why we couldn't do artificial photosynthesis. Let's do it. And a lot of people were reading the article and started to work on that. And then the price of oil dropped. And all the funding for that area of research was wiped out, coincided with some events in 1980 in the US. And we stopped for about 25 years. We stopped working on that problem in any systematic way. That was probably a very bad decision. So, okay, here we are later facing these deep environmental problems where we're changing the world because of how we're using fossil fuel in ways that are unpredictable and posing risks to the future of humanity, perhaps bracketed risks, perhaps not. Now would be a very good time to stay focused on this problem and have people really go at it. I presented here because I'm more of a basic fundamental scientist, not so much of a technologist. I presented my thinking on how one might approach it. But a lot of people, there might be answers out there that are practical even sooner that I don't know about. I think this is one of the big problems, to figure out how to store the energy. We should go after it, and I think it'd be a great research problem for scientists here in Greece because there's a lot of photons. Yes?
Yes, I'm following after. What's your opinion about CTV with mirrors like this?
Yes.
And molten salt? We're working on that.
Yeah. Yeah. So the question is about concentrated solar power. So there are a number of ways in which it's possible instead of just having a planar surface and having the photons hit that surface and collecting it, you can have a mirror and concentrate the light down. And it's a worthy area of research. It hasn't gained traction commercially compared to the ordinary way. But you know, a few months ago I was in Saudi Arabia in the desert, and I saw an installation where they were doing some amazing concentrated PV work. And yeah, you think, okay, maybe. I mean, you know, so there's some practical issues there about can you get the story, you know, but it's certainly worthy of looking at. And then on the molten salt topic, I mean, there are a variety of ways in which potentially you can store the energy temporarily to even out the nighttime and the daytime. And these are by having, say, a material that you know, can store the heat, and then you can run, say, a regular conventional heat generator throughout the night, and so on. And look, those things are also interesting, and it's competitive to try and see how far one can take it. My own bias is sort of what I said. And my bias is not so much technical. That's why I would say engineers should not listen to what I'm saying right now. But my bias is more from the scientific point of view. To me, when you think about the photon as this quantum object, you don't want to just lose that to heat. What you want to do is learn how to rearrange those chemical bonds to states of lower entropy, and now the energy is locked in to whenever you want to use it. So that's just my personal bias. These other approaches should be part of a, you know, a lot of different ideas that people try, and we'll see which one turns out to be better.
You mentioned about inventing the nanoparticles in Rome, and wondering, like, you have the nanoparticles like in rods, carbon nanotube arrays, you invent all these nanoparticles that have an efficient photosynthesis system. Or maybe the same system can be for catalytic membrane, for sea oxidation. But even in the solar system, you can golden nanoparticles. You can have a solar system where it can avoid agglomeration as well, nanoparticles, make the arrays for the solar cell.
Yeah. Look, I mean, absolutely. You know, one of the things I would say is that the nanoscience field went through a period of time of developing fundamental building blocks. So nanocrystals are one, nanotubes are certainly another, and there's a list of them. They're all nano objects, wires, and so on. And the early stages of nanoscience consisted of just really learning how to make and control those nanoscale objects. And that phase is now very advanced, very, very advanced. So the issue now is how to integrate those together into functional units that have greater, now the question becomes what level of precision is required when you assemble them together. So in some scenarios, people just mix it all together. I'm more in the, I would like to really precisely control all the positioning. That's my bias. I couldn't tell you which is better. Again, it's a very active field with lots of great stuff happening. So there's a question in front here.
Lose a minute of the time. You've seen photosynthesis has been a process that made land life possible, and can be used for purifying the air, for changing the temperature of the oceans, and then we don't need land. We could have vertical applications with the oceans. Why are we losing time? Why is it not placed as a priority in policy? Are people hiding from each other and they want to put it as a priority, or what is happening? Because we speak about solar energy and all that, but photosynthesis can be the quick way.
So, you know, photosynthesis definitely is an important piece, and there's a lot of great work going on to try to harness the biological systems for these purposes. And It's getting better. There's more happening there. You look at some of those things. But, to your point about being in a hurry, so this is the problem that we have been facing, is that the climate change problem has been a difficult one for society to adapt to mentally. And, there are many reasons for that. Among them are the fact that energy is the biggest industry in the world. And that means that it takes actually, because of that, because of the size, even if there was a determination to make a change, it takes a long time. Just to build energy systems takes a long time. It's just, the infrastructure is so massive. To give you a feeling for that, the 33 gigatons of CO2 emitted is 60 times more than the top 100 chemicals produced in the world. So if you take bulk chemicals, take the top 100 of them, multiply by 60, it's absolutely almost a mind-boggling size. And so, it is certainly true that reaching a consensus in society about how to deal with a problem of this scale has been difficult and slow. And part of it is because the dialogue with society is very difficult when it's not easy to make, scientists cannot easily make definitive statements. They can make probabilistic statements. They can say there's a certain probability that X, Y, or Z will occur. But the political system, particularly when there's large existing financial interests, really has a very hard time responding to that. My sense, that's why I have a version of the talk that I do give where I just describe the science of climate change. And I give that a lot in the United States. And, I think I remain optimistic on this topic because every time we have more discussion about it, more people understand the underlying science and how really ironclad, inescapable the conclusion is that the risks of not making big changes are really significant. So I'm optimistic, and I also feel like it is possible for us to make a future in which the carbon cycle is plausibly balanced without completely trashing the planet. So I remain an optimist, despite the fact that there is a lot of rancor around the topic, and not everybody is in complete agreement. We just have to keep putting out the facts, and it will eventually change. Soon enough, even, I hope that the really bad consequences won't materialize. I'm an optimist. Hope is not a strategy.
Can you predict any major developments that will change the landscape of this technology in the next 10, 15 years from what we have right now?
Yeah, so the question is, will there be abrupt changes in the technologies? And, it's fascinating how quickly things do change. For example, the determination of the Chinese to enter the solar market has produced changes in solar energy that have left literally hundreds of companies going into bankruptcy. So in the solar energy field, it's both the best of times and the worst of times. And part of that is because people didn't expect that it would be possible to bring the price of making a crystalline solar cell down as quickly as it has come down. Now, there's a lot of arguments. Some people say, well, the Chinese are dumping. Actually, I think what happened is they just they got very enthusiastic and they made more capacity than what even this fast-growing market is capable of taking up, so the prices have dropped a lot. That's an example of something which, I mean, you could have talked to all kinds of people, including me, 5 years ago, would not have realized that that was the case. So, I mean, it is a pretty rapidly changing area. This is one of the things that makes it a little hard, again, for society to understand how to handle it, because the kinds of things that I described do take time, and yet there are changes that take place in the system periodically that are unanticipated. And, you know, we had the big oil shock in the 70s, and then all of a sudden production went up and the prices dropped. And then, so, you know, I guess what I would argue is I have no doubt there are going to be a bunch of surprises. But the nature of these problems are sufficiently deep and sufficiently long-term that my real hope is that we could have a policy that stays consistent on trying to solve the underlying problems for long enough that we would actually get the outcome that we want. I'm hoping that that's true. That's another one of my optimistic kind of, you know, projections. There's one right there. That one. Yeah.
Does it mean that by replicating the photosynthesis process, we'll be able to produce fuels of different types as well?
Yes, that's the intent. In fact, if we get good at artificial photosynthesis, it would allow us to have ways of making chemicals, which we're going to desperately need as we deplete the sources of where we get most of our chemicals from, you know, over time eventually. And so, you know, that in fact may be, in reality, artificial photosynthesis may find its first toehold in a technology that's not related to energy, but to some other type of chemical use, and then grow from there. That's possible.
And to follow up on this one, you mentioned in passing that you like the dots because you can control them better. So by doing this, by using the quantum dots to do this artificial photosynthesis, you can understand the scaling laws better, you can control, is this what you meant?
Yes, that's my perspective on it. As I would like, from my perspective, I want to be able to design the materials from you know, an understanding of the principles of how they work. And in my area, that means exploiting all of the scaling laws, playing them off against each other, and then getting just the right thing. That's the game that we like to play in my area.
Do you fabricate the dots?
Yes. No, we fabricate all of the dots. And actually, if you have, I'll just tell you one thing. I just wanted to, no, I skipped it, it's gone now. But what I wanted to just say briefly was we do a lot of dot fabrication, and in fact, it's one of, I didn't get to show it, but we learned over a period of time how to make not just simple shapes like dots and rods and disks, but we learned how to make crystals that are branched and striped and hollow and nested. And that was one of the funnest times I ever had. You know, the 10 years when we did that was making all of these funny shapes and types and finding out how to do that. It was really fun. It was for no useful purpose, but it was really a blast. Yeah. Okay, so we do.
Assuming you are close to development and applied development, on the issue of cost of nano-produced solar cells, can you give us any indication of what you expect it to be?
Cost of a nanoparticle-based solar cell? Well, you know, I don't know.
You have to assume grid parity at some point.
Yeah, what's so interesting is that, you know, I had not thought that a crystalline silicon solar cell would be anywhere close to grid parity, but it's getting pretty darn close at this point. In fact, in some parts of the world, it's already at grid parity. So that's fascinating. And so that takes all of the things like what I described, or the organic solar cells and so on, and it puts them in a bit of an awkward position where at one point we would have just argued, let's build on the dollar side of the dollar per watt equation and we'll be much cheaper. But the terms of that debate are changing, and we're going to have to start thinking about, can we do things on the watts side? In other words, to exceed the efficiency of silicon. And it turns out, you know, it would be presumptuous for me to say that a nanoparticle solar cell is going to beat out silicon, because it's not even close today. But actually, there are some scaling law arguments that say maybe we could. And so, you know, it's a research project. I don't know, you know, I can't tell you the answer.
About 15 years ago, there was a conference at Tsinghua University I attended, and I spoke to about actually taking advantage of Moore's law on semiconductors to basically the same thing, solar cells, which are basic semiconductors.
Yeah.
And the Chinese knew from the beginning that you had to take advantage of that. So if you are looking at a moving target, you must also be aware that you can achieve the same with nanoscale. So
Yeah.
perhaps that would be a good point to start at.
Yeah, I agree.
Thank you.
Okay.